Good morning, everyone. So, we will just take up whatever we have left in the last class. In the last class, we were discussing about the similarity solution, and we have seen that there are several transient as well as two-dimensional steady state problems can be solved using similarity solution. Now, we have discussed about the criterion of having similarity solution of a particular differential equation, and the thumb rules we have found out that the nature of the equation has to be parabolic. That is one condition. The other condition is that one of the boundary condition must be residing at infinity. If these two conditions are met, then you may be having a similarity solution of the governing equation. So, we have solved the Stokes' first problem to illustrate how to use similarity solution, how to obtain the similarity parameters, so on and so forth. So, we have started in fact discussing a second example, that will be the basically a growing concentration boundary layer over a porous ball. It may be a membrane surface. So, we will continue the discussion and get the complete solution today. So, the problem we are discussing about let us look into the system. You are having a rectangular channel, a channel with a rectangular cross section. Okay. Cross section, and it is a very thin channel, that means the height is very small. Now, our y axis is from the bottom surface facing the top, and this is x axis. The length of the channel is x equal to 0 and x equal to L. Now, half height of the channel is small h is the half height, full height is twice h. Now, we are you are placing a porous surface at the porous the bottom plate is basically porous. You can put a membrane surface or whatever to facilitate any filtration operation, and you pump the feed containing some solutes which will be having molecular size larger than the pore size of this membrane or porous surface. So, the solutes will be retained by this membrane, and it will be developing a concentration boundary layer over the membrane surface, right. So, the basically the you are applying pressure, solutes will be deposited over the membrane surface. As you go downstream, the thickness of this boundary layer or concentration boundary layer will be going on increasing. At the very beginning, it is uniform concentration everywhere. Now, after this, after let us say this is effective length x equal to let us say this point to that point. Okay. So, you are taking out water, there you are applying a pressure. This pressure is in the order of 7 to 8 atmosphere. Pressure inside the feed chamber is in the order of 7 to 8 atmosphere pressure. Yes. Right, you are applying a pressure, so that the pressure is around 7 to 8 atmosphere. Now, because of the pressure, the solutes will be convected towards the membrane, and it will be, and since its molecular size is larger than the pore size of the membrane, it will be retained by the membrane, and you go downstream, more solutes will be deposited. Now, this thickness of this concentration boundary layer will be slightly increasing, but it will not be going on increasing, because you are applying the feed in this direction. The feed is flowing from the inlet towards the outlet. So, there will be a shearing motion of the feed over the membrane surface. So, the growth of the concentration boundary layer will be limited. It cannot go on increasing unbounded. So, it will be bounded after certain distance, and it will be almost reaching a plateau value. Now, the solvent transport, that means the flow of water through this membrane surface, will be inversely proportional to the thickness of this concentration boundary layer. More with the thickness of this layer, more resistance it will offer against the solvent flow towards the membrane. So, initially, since this deposition is very small, you will be getting the maximum permeate flow rate. This side is called permeate, that is being permeated. The thickness of this boundary layer increasing, so the flux is decreasing. Okay. So, continuously you are going to get the very small permeate flow rate. Now, permeate flow rate is described as VW, water velocity. It is almost it has a unit of velocity. It is basically volumetric flow rate, volumetric flow per unit time per unit membrane area. Okay. So, it has a unit of meter per second, or basically it has a unit of velocity, permeate velocity. Okay. And how you are determining, you are measuring the volumetric flow rate, you are putting a measuring cylinder and time out for a particular for filling of, let us say 5 ml or so. So, you will be getting the volumetric flow rate and you know the membrane area. So, you will be getting the permeate velocity. So, that is a measurable quantity. Now, our aim is to find out so basically within this thin boundary layer, concentration boundary layer, and let us say at any point this height is delta, okay, and order of magnitude of this delta is typically in the order of 10 to the power minus 6 meter or in the order of micron. Okay. Whereas, your half height is having some measurable distance. So, compared to half height, this distance, this thickness 0 to delta will be extremely small. Inside this concentration boundary layer, the concentration profile exists. That means, there is a profile of concentration as a, there is a variation of concentration as a location, as a function of location x and y. Beyond this concentration boundary layer, C is equal to C naught, that is the concentration of the feed. So, basically within the boundary layer there is a change in concentration, or there is a concentration profile exists within the boundary layer, concentration boundary layer. Beyond that there is no variation of concentration. So, whatever the governing equation you are going to write down for the concentration profile within this boundary layer, that will be valid from 0 to delta. Beyond delta, any y greater than delta, concentration profile is C is equal to C naught. Now, although we discussed, I mentioned this thing in last class, also this thickness is in the order of micron. Whatever the mass transfer taking place, it takes place within that very small distance. So, basically you are writing a governing equation to I would like to tell you the objective of this exercise. We would like to find out concentration profile as a function of x and y within this boundary layer. From that information, we will be calculating what is the mass transfer coefficient. From the mass transfer coefficient, you will be able to find out how much mass has been transported from the bulk to the wall, or vice versa, in which direction the concentration gradient exists. Okay. Now, in this problem there is a trick. Now, the trick is we are considering a channel of, let us say, length x equal to 0 to x equal to L, where L will be typically 1 meter or more. Okay. Now, there is something called entrance length. What is entrance length? Entrance length is basically a length within a conduit where there is a variation of velocity. The velocity of the fluid will be varying as a function of cross section. Beyond that particular length, it will be fully developed flow. The velocity of the velocity profile will look something like this. It will be flat here, it will be something like this, and after this it will be a parabolic velocity profile as usual. So, let us consider laminar flow rate. Okay. So, up to this distance your boundary layer is developing. This boundary layer is velocity boundary layer or hydrodynamic boundary layer. That boundary layer we are discussing previously, it was a concentration boundary layer. 3 boundary layers can coexist: concentration boundary layer, thermal boundary layer, and velocity boundary layer or hydrodynamic boundary layer. Okay. Now, in this problem it is a case of isothermal, it is an isothermal case. So, there is no temperature variation and there is no question of thermal boundary layer. Now, boundary layer is developing from both the sides of the velocity boundary layer, and beyond a particular length both the boundary layers will merge, and throughout the whole cross section you will be getting the boundary layer. Okay. So, in that case the velocity is fully developed under the laminar flow condition, and that will be the parabolic velocity profile that will be existing rest of the channel, and you know how what are the derivation. Okay. So, this length is called entrance length. Okay. Now, you can estimate what is the value, numerical value of this entrance length. The formula is LE by DE is equal to 0.05 Reynolds number based on equivalent diameter. Okay. If it is a circular pipe, equivalent diameter will be diameter of the pipe. If it is a not circular, you know how to find out the equivalent diameter. In the last class I have derived what will be the equivalent diameter for this particular case. Now, the maximum Reynolds number will be around 2200 for the laminar flow. Okay. Let us say you put it 2000, and the channel height is around in the order of 0.1 millimeter. Okay. If you put that, your entrance length will be coming out to be 4 centimeter. Okay. That means, if you consider a channel of length 1 meter for initial 4 or 5 or 6 centimeter, the flow is developing, the hydrodynamic boundary layer is developing, beyond that it is completely developed. Okay. So, basically to ease out your analysis, because the concentration, the velocity profile you know beyond this entrance length is purely parabolic. You know, before this entrance length, this particular distance x equal to LE, the velocity profile will be complicated. So, what the best thing you can do, you put a plastic sheet over here for the let us say 6 centimeter. Okay. So, there is no effect of suction, the membrane is covered, there is no effect, you are not taking out any water. So, there is the concentration profile, what is concentration distribution, uniform distribution that is entering, it will be same as C naught throughout up to the whenever it will be travelling over the covered portion. After the covered portion, the velocity field is fully developed, and you are taking out water from here, and there will be deposition of the concentration solute particles over the membrane surface. So, in this problem we cover the initial 5 or 6 centimeter of the membrane surface and allow the feed water feed solution to come into it, and let us put our axis here x equal to 0 to x equal to L, that will be in the order of 1 meter or several meters maybe. So, you will be getting a developing concentration boundary layer throughout your channel, whereas your hydrodynamic or velocity boundary layer is fully developed, right. This is the velocity boundary layer, this is the concentration boundary layer that is developing. So, it is a problem of developing concentration boundary layer or mass transfer boundary layer and fully developed velocity boundary layer or hydrodynamic boundary layer. We have covered the initial first 5 or 6 centimeter, because we know the velocity profile of fully developed hydrodynamic boundary layer that we are going to use for our subsequent calculations. Okay. Only that purpose. Okay. Now, it is a case of steady state flow. Okay. And let us look into any fluid particle that will be experience what are the forces. One will be the fluid particle will be the solute particles will be experiencing a convective flux towards the membrane because of the pressure. Because of pressure you are getting the suction. Okay. So, there will be a convective flux. What will be that? That will be Vw into C. Okay. Let us say V times C. V is the velocity in the y direction. It should be negative V, because y direction is up. The concentration of the solutes will be more on the surface because they are retained. So, concentration will be less in the bulk. So, there will be a concentration gradient existing from the surface towards the bulk. So, there will be a backward diffusion. So, one will be there will be convective force that will be acting on the solute particles. At the same time, there will be backward diffusive flux. Diffusive force, because the concentration gradient del C del Y existing in your system. Now, at the steady state, at the membrane surface, these two fluxes will be equal. At the steady state, these two fluxes will be equal, and there will be a steady state existing in your system. So, our aim is, objective of this work is to find out concentration as a function of x and y within this concentration boundary layer, and then evaluate C at the membrane surface, that is at y equal to 0, evaluate del C del y at the membrane surface, that is at y equal to 0, and estimate the mass transfer coefficient or Sherwood number. Okay. Now, what we should write now? We should write a species balance or component balance within the concentration boundary layer. Now, if you write down the species balance, the form will be U del C del x plus V del C del y is equal to d del square C del x square plus d del square C del y square. There will be no generation, no consumption of the species, because it is not a reactive system. And these will be the convective parts, convective terms, and these will be the diffusive terms, and it is a steady state problem. So, del C del T will not be present. Okay. Now, this equation is valid within the concentration boundary layer, that means for 0 to delta, right. Now, the diffusion in there is the convection in the x direction is given by this term U del C del x. The diffusion in the x direction is given by this term d del square C del x square. In fact, the variation of concentration in the x direction will be extremely small. So, or in other words, the U, typically the order of magnitude of U cross flow velocity or the velocity in the x direction, the cross sectional average velocity will be in the order of 0.3 meter per second to 0.5 meter per second. Okay. And we are talking about the system where the solutes are like protein, high molecular weight polymers, something like that. So, in fact, they will be having a diffusivity in the order of 10 to the power minus 11 meter square per second. So, compared to the convection in the x direction, the diffusive term in the x direction will be extremely small, because of the two facts. One is d itself is very small, first one, and second one is the concentration variation in the x direction will be extremely small, and U, the magnitude of U will be very high. So, because of that reason, you can say that convection in the x direction will be very large compared to the diffusion in the x direction. So, in that case, your governing equation will be simplified. It will become U del C del x plus V del C del y is equal to d del square C del y square. Now, if for the solution of this problem, you require one condition on x and two boundary conditions on y, right. The condition on x will be at x equal to 0, you are having the feed concentration C is equal to C naught, at y is equal to delta, some delta, at the edge of the concentration boundary layer, C is equal to C naught, and at the membrane at y equal to 0, that means at the membrane surface all the at the steady state all the fluxes towards the membrane will be equal to 0, right. So, there will be a flux V times C and there will be a minus V times C, right, or you can put V equal to minus V W later on, or and you will be having a flux d del C del y in the opposite direction minus. Okay. So, it will be basically V C minus d del C del y will be equal to 0. Now, can you identify this boundary condition? It is basically a mixed boundary condition that we have talked previously. Robin, mixed boundary condition. Okay. Now, you have formulated the problem, you have formulated the governing equation, you have formulated the boundary conditions, the relevant boundary conditions. Now, what is left is the insertion of velocity profile u and v. Okay. Now, let us look into the velocity profiles. Now, first look into the x component velocity. X component we have assumed it is completely developed flow. So, the parabolic profile that is existing here u is equal to 3 by 2 u naught 1 minus y minus h by h whole square. Okay. That is the corresponding parabolic velocity profile that will be existing in the laminar under the laminar flow condition within a rectangular channel. The counterpart of this in a tube is 1 minus r square by r square. Okay. Now, let us see, this will be further simplified that the concentration boundary layer, thickness of the concentration boundary layer. Now, you are talking about the solutes of proteins high molecular weight polymer which will be having extremely low diffusivity. Diffusivity will be in the order of 10 to the power minus 11 meter square per second. Now, let us look into the Schmidt number. Schmidt number is mu by rho d. So, let us take it as the water values. Water viscosity is 10 to the minus 3 Pascal second, density is 1000 kg per meter cube, and let us say 10 to the minus 11. So, it will be coming out to be 10 to the power 5. Schmidt number will be 10 to the power 5, and the thickness of the concentration boundary layer delta is inversely proportional to Schmidt number. Okay. Since Schmidt number is pretty high, the thickness will be extremely small. So, in this particular case, the thickness of concentration boundary will be very small. That means, the governing equation whatever we are writing, since this is valid for the region 0 to delta, where the delta is the thickness of the mass transfer boundary layer at any x location. Since this thickness is very small, the velocity profile, let us look into what happens to the velocity profile. The x component velocity profile will look something like this. I am just exploding the diagram. This will be the parabolic velocity profile, okay. And we are talking about the mass transfer boundary layer something like this. So, our governing equation is valid within this region. That means, the velocity profile you are considering, it will be basically linear portion of this parabolic profile. In other words, the term y square by h square within this concentration boundary layer will be extremely small compared to y by h, because the thinness of this concentration boundary layer. Okay. So, if that is the case, now let us look into how it will be simplified. U is equal to 3 by 2 u naught 1 minus y minus h by h. So, it will be y by h minus 1 whole square. Okay. So, it will be 3 by 2 u naught 1 minus y square by h square minus plus 2 y by h minus 1. Okay. So, 1 will be cancelled out, and since this the governing equation in the governing equation y is pretty small compared to half height. So, we can neglect y square by h square compared to y by h.
Why are you talking delta?
The maximum value of y is delta. The maximum value of y is delta, right? The maximum value of y is delta, and in fact, you are solving the governing equation concentration profile within the boundary layer. Beyond the boundary layer, C is equal to C naught uniform. So, there is no question of solving any equation there. So, y square by h square will be very small compared to 2 y by h. So, this will become 3 by 2 3 u 0 y by h. That means, u is equal to nothing but k times y, u 0 is constant, h is constant. So, it will be k times y, it is basically a linear profile. So, this is a linear portion of this parabolic profile we are discussing. Okay. And y component velocity, since this boundary layer is extremely small, y component velocity can be approximated as whatever the velocity you are getting here, the same velocity profile is existing there, because of the fact this thickness will be extremely small. Although there will be slight variation, but those variations will be really very minute. So, V is roughly minus V w there. Okay. V w is the measurable flux that you are getting out of the membrane surface, and since we said earlier this is increasing as a function of x, the resistance against the water flow rate towards the membrane will be varying. More be this thickness, less will be the flux. So, flux will be maximum, flux or permeate velocity, whatever the way, because it has a unit of velocity. It will be maximum here, because this thickness is minimum there. Then the thickness increasing, the permeate velocity is decreasing. So, it will be a function of x. Okay. Now you insert this velocity profile in your governing equation, and let us see how it looks like. Now, your governing equation becomes u del c del x, that means 3 u 0 y by h del c del x plus v del c del y minus v w del c del y is equal to d del square c del y square. This is the equation you are going to solve. Okay. Now, let us look into the boundary conditions. At x equal to 0, your c is equal to c naught, at y is equal to delta, c is equal to c naught, at y equal to 0, v is equal to minus v w, put that v w c plus d del c del y will be is equal to 0. Okay. Now, the point comes about this boundary condition. You have formulated a governing equation, you have formulated boundary conditions. Now, this particular boundary is unknown to you. Over and above, it is a case of varying boundary, because delta will be function of x. Not necessarily you do not know the value of delta, you do not know the value of delta, because value of delta is also varying at different x locations. Since this thickness is very small compared to physical dimensions of the channel, you can replace this boundary condition as y equal to infinity. So, this will be equivalent to y is equal to delta, y equal to infinity, c is equal to c naught.
So, you said it's very small compared to the thickness.
Right.
So, why infinity?
So, if someone, suppose this is the half height, and this will be in the order of millimeter, the order of micrometer. So, if someone is standing here, any observer is standing there even in the channel mid channel height, he does not experience the existence of this boundary layer. But because of the boundary layer, all the mass transfer is taking place within that small distance, small thickness. So, safely it is exactly the same logic we have done in the previous problem, Stokes' first problem. So, this boundary condition y is equal to delta will be replaced by y equal to infinity, c equal to c naught. Okay. So, now this the governing equation is a parabolic one. This will be having a boundary condition at infinity. So, you will be having a similarity solution for this particular case. Okay. Now, let us look into the similarity solution. Any problem like this, the first step will be evaluation or estimation of the similarity parameter. If you do not know the combined variable, the functional form of the combined variable, you cannot proceed further. Similarity variable or similarity parameter. For that, we adopt the same rule that we have done in the previous class. We evaluate the governing equation at the edge of the boundary layer. Concentration boundary layer. Okay. If you do that, 3 u0 y by h del c del x, and at the edge of boundary layer you have already learned about the boundary layers. The dependent variable, the value of that will be equal to the free stream velocity, free stream value. If it is a velocity boundary layer, v is equal to v naught, u is equal to u naught, u infinity at the edge of the boundary layer, c is equal to c naught, t is equal to t naught, and the variation of the dependent variable with respect to the normal direction will be equal to 0. These two conditions have to be satisfied whenever you are talking about the boundary layer. At the edge of the boundary layer, c is equal to c naught and del c del y will be equal to 0, right. So, since del c del y will be equal to 0, the second term will be off. So, this will be roughly equal to d del square c del y square. Okay. Now, starting from x equal to 0 to any x location, let us see this x equal to 0, this is at any x location, and at this x location your value of concentration boundary layer is, let us say, delta, some arbitrary delta. Okay. If you put that 3 u0 y is delta divided by h, del c is delta c within x equal to x and x equal to 0. So, this will be delta x means x minus 0, that is x roughly d delta c, and this is delta square. Del square c is again a difference of concentration that we have. What?
Del c or del y you said 0 at y put delta.
That does not mean that the second derivative will be vanishing. Okay. So, delta c will be gone. So, it will be delta cube is roughly is equal to dh x by 3 u0. Okay. So, delta will be cube root of dh x by 3 u0. So, that is the variation of delta with respect to x. It will be proportional to x to the power 1/3. That means, the concentration boundary layer will not be developing linearly, it will be developing with a functional form proportional to x to the power 1/3. Okay. Now, what is the similarity parameter now? The similarity parameter is generally defined as eta as y by delta. Okay. So, that means this ensure, this functional form will ensure that every x location the profiles are self similar, the profiles are similar. Okay. So, eta is y by delta. So, y 3 u0 divided by h dx raised to the power 1/3. Okay. So, this will be the functional form of eta. Now, if you just put the dimension, you will just you can find out, you can check out that eta is a dimensionless variable. This is it has no dimension. Okay. Now, once you, so basically eta will be having a functional form y by x to the power 1 upon 3, and all these constants will be appearing here to make it non-dimensional. Okay. Now, what is the next step? Next step is you get the partial derivative of your governing equation with respect to eta, and change all the independent variables with into single variable eta, so that your partial derivatives will becomes full derivative, complete derivatives. Okay. Now, del c del x will be del c del eta del x, right, and del c del eta will be a complete derivative. So, it will be d c d eta times del eta del x, and del eta del x you can find out and this whole thing del eta del x, if you can find out, there will be, I am just omitting couple of steps, this will becomes minus eta by 3 x d c d eta. Okay. Just take the derivative of del eta del x. Okay. It will be x to the power minus 1 by 1 upon 3 will be coming in the front, and it will becomes x to the power minus 4 by 3, and then you can combine, you will be, that will be in this form finally. Okay. Now, find out the other derivatives, del c del eta, del c del y. Del c del y will be d c d eta del eta del y. What is del eta del y? Del eta del y will be 3 u 0 by h dx raised to the power 1 upon 3. Okay. Del square c del y square, one more derivative of this, del y of d c d eta del y of this. So, it will becomes, in fact, del y of the whole thing. So, it becomes del eta del y again. So, it becomes d square c d eta square, one more term of this. So, it becomes 3 u 0 h dx raised to the power 2 by 3. Okay, simple derivatives. Now, once you get all these derivatives in terms of similarity parameter, you can substitute these values in your governing equation, and your governing equation now turns out to be an ordinary differential equation from a partial differential equation. Okay. Now, we substitute this partial derivative. Governing equation. Okay. If you do that, the form will becomes 3 u 0 y by h, that is u del c del x minus eta by 3 x d c d eta minus v w 3 u 0 h dx raised to the 1 upon 3 d c d eta is equal to d del square c del y square 3 u 0 h dx raised to the power 2 by 3 d square c d eta square. Okay. Now, these will be, you just take you just make it, you divide both sides of this equation by d and this raised to the 2 by 3, and after simple algebraic manipulation or simplification, the final form of this equation becomes, I am omitting couple of steps, these are all basically algebraic manipulation, you can do it by yourself if you just sit down with a pen and paper. Final form becomes minus eta square by 3 dc d eta minus v w by d h dx by 3 u 0 raised to the power 1 upon 3 dc d eta is equal to d square c d eta square. Now, I request all of you to get this final form from this equation, or in fact, you should get all the derivations by yourself. Okay. Now, here is again there is a trick that what is the, as we have discussed earlier, the permeate velocity will be inversely proportional to the thickness of the concentration boundary layer, right. That means, V w is inversely proportional to 1 by delta, V w is inversely proportional to delta. Okay. So, more with the thickness, less with the permeate velocity, because it will be offering more resistance. So, V w delta will be right, it will be constant. And what is delta? Delta is proportional to x to the power 1 upon 3. Delta is proportional to x to the power 1 upon 3. That means, V w x to the power 1 upon 3 is a constant. That is correct. If that is correct, V w x to the power 1 upon 3 is appearing here, and all these are basically some constants. Okay. And if you see, this whole thing becomes non-dimensional. If you just check the dimension of this whole thing, it becomes non-dimensional. So, it becomes a non-dimensional constant, because of the argument that V w x to the power 1 upon 3 is a constant. Okay. Let us call this constant to be A. So, A becomes V w by d h dx divided by 3 u 0 raised to the power 1 upon 3. So, this becomes V w h x 3 u 0 d square, you can take d inside raised to the 1 upon 3. Okay. Now, this is a constant and that constant is A. Now, how to find out that constant is a different issue. Let us look into the solution now. Now, the governing equation becomes minus eta square by 3 dc d eta minus A dc d eta is equal to d square c d eta square. Okay. Now, eta is a dimensionless parameter, A is a dimensionless parameter, constant, only C is a dimensional stuff. So, let us make it non-dimensional, nothing you have to do, you have to divide both sides by C naught. So, let us define C star is equal to C by C naught. If you do that, then it becomes d square C star d eta square is equal to minus eta square by 3 minus A d C star d eta. So, this is a fate of your governing equation, which was a parabolic partial differential equation. It has become a second order ordinary differential equation. Now, to solve the problem, you need to have two boundary conditions on eta. For that, you have to change the original boundary condition into the transformed parameter eta. What is that? At y equal to infinity, C was equal to C naught. At y equal to infinity means at eta equal to infinity. C star is equal to 1, right. At y equal to 0, that means at eta equal to 0, you have the boundary condition V w c plus d del c del y will be equal to 0. Now, you have already expressed the partial derivative del c del y in terms of dc d eta, substitute that, because the boundary condition has to be in terms of eta. Okay. Del c del y was dc d eta V w c plus d del c del y was 3 u 0 h dx raised to the power 1 upon 3 dc d eta, right. Okay. Now, what is this? VWC plus 3 U0. No, D is there, no, D del C del y plus VWC. Just look into the boundary condition at y equal to 0. So, 3 U0 D square by Hx raised to the 1 upon 3 dc d eta.
That's what I'm saying. We can manipulate this and write AC plus DC by dt.
Exactly, that I am going to write it. This was nothing but A. Okay. So, VWC plus A dc d eta is equal to 0. No, AC, right. VW by that thing, right. Perfect. Very good. Okay. Now, A is again non-dimensional parameter, eta is also non-dimensional parameter, divide both sides by C and it becomes C star. So, dc star d eta plus A C star is equal to 0. This is the transform boundary condition at y equal to 0 in terms of eta. Now, you are able to solve the your governing equation. What was that? All right, this one. D square C star d eta square is equal to minus eta square by 3 minus A d C star d eta. For that, you just put d C star d eta is equal to z. This becomes dz d eta minus eta square by 3 minus A z. Okay. Separate the variables dz by z minus eta square by 3 minus A d eta. Okay. One integration will give you z C1 exponential minus eta cube by 3 minus A eta. Okay. What is z? Z is nothing but d C star d eta, right. One more integration will give you C star as a function of eta as C1 exponential minus eta cube by 3 minus A eta d eta plus C2, where the constant C1 and C2 are the integration constants. Now, this C1 and C2 can be evaluated from the two boundary conditions at eta equal to 0 and eta equal to infinity. Okay. At eta equal to 0, at eta equal to 0 means what is C star? This will be from 0 to 0. So, this whole integration will be gone, the C star will be nothing but C2 at eta equal to 0. So, at eta equal to 0 you have C1 plus AC2 is equal to 0. Am I correct? No. DC star d eta plus AC star. Acha. Right, there is one more term, right. The C star will be equal to C2 at eta equal to 0. And what is DC star d eta? Are eta equal to 0? DC star d eta will be C1 only, because exponential 0. So, that will be 1. So, DC star d eta will be equal to C1, right. So, at eta equal to 0 you will be getting C1 plus AC2 is equal to 0. Everyone is convinced? Okay. Let us look into the boundary condition at eta equal to 0. At eta equal to 0, your DC star d eta plus AC star was equal to 0, right. And what is your C star? C star is nothing but C1 exponential minus eta cube by 3 minus A eta d eta plus C2. At eta equal to 0, C star will be equal to C2. So, this will be C2. What is d star d eta?
That is C1.
Right, that will be z. D star d eta was z, and it was C1 exponential function of eta. So, eta was 0, so that means whole thing exponential of this thing will be 1. So, d star d eta will be equal to C1. So, C1 plus ACT is equal to 0. Okay. Now, let us look into the other boundary condition at eta equal to infinity. At eta equal to infinity, your sister was equal to 1. That means, C1 0 to infinity exponential minus eta cube by 3 minus a eta d eta plus C2 is equal to 1. Okay. Now, you see this is a definite integral, it will be returning you a value once you know the constant a. This is a definite integral 0 to infinity, right. Let us call that integral to be I. So, I will be 0 to infinity exponential minus eta cube by 3 minus a eta d eta. So, at the boundary condition at eta equal to infinity becomes C1 I plus C2 is equal to 1. Okay. Now, you have the one equation previously, you have this equation now, two equations and two unknown C1 and C2, and C1 becomes minus A 1 minus AI, solve this two equation, and C2 becomes 1 by 1 minus AI. So, if you know the constant A, you will be find out you can find out sister as a function of eta. And what is eta? Eta is nothing but y by x cube. So, at various values of y, for a fixed value of x, you can get a series of various eta. So, you can have sister as a function of x and y. Similarly, for various values of y, for a fixed value of y, sister can be found out at various values of x. In other words, you can find out for any combination of x and y the value of sister. So, sister as a function of x and y can be evaluated from this equation, because you have already evaluated C2, you have already evaluated C1, provided you know the constant A. Suppose that is known to you. How that will be known to you? Let us look into the value of A, derivation of expression of A, right. A is nothing but VW into h x cube divided by 3 u0 d square. That means, VW can be written as A 3 u0 d square h x raised to the 1 upon 3. Okay. Now, what is VW? VW, this basically gives VW as a function of x at different x location in the channel. But in an actual experimental setup, you cannot, it is not possible to measure permeate velocity at every x location. So, what is generally done? It is generally you collect all the x location, at the middle of the channel you put a tap from where the permeate is coming, and you put a measuring cylinder and measure the volumetric flow rate. Per unit membrane area, you will be getting the permeate flux, permeate velocity. So, it is basically length averaged velocity. So, what is length averaged velocity? 1 by L 0 to L VW as a function of x. Okay. So, 1 by L 0 to L A 3 u0 d square by h raised to the power 1 upon 3 x to the power minus 1 upon 3 dx. So, it will be 1 over L A 3 u0 d square by h raised to the 1 upon 3. This will be minus 1 upon 3 plus 1. So, x to the power 2 by 3, L to the power 2 by 3, 3 by 2, 1 upon 5, 1.5. That is correct? Okay. So, it will becomes 1 over L. So, L to the power 1 upon 3 in the denominator. So, everything will be going inside 1.5 a 3 u 0 d square over h l raised to the power 1 upon 3, right. So, from here you will be getting a as this 3 by 2. So, it will be 2 by 3.67 h l 3 u 0 d square raised to the 1 upon 3 v w. That will be the expression of A. V w means is a length average V w. So, you measure the permeate velocity. So, it is a measurable quantity. You have already measured V w bar, h is a dimension, L is the dimension, U 0 is the operating condition, D is the property of the solute that is known to you. So, once you know the measure the length average permeate velocity, A will be known to you, right. Once A will be known to you, you can put A in the concentration profile and find out C as a function of x and y. How to translate or interpret that result in order to estimate the mass transfer coefficient, that we will look into the next class. Okay. Thank you. Good morning everyone. So, we were discussing about the similarity solution and how to use similarity solution in various chemical engineering application. The latest application that we are talking about, that was flow through a channel closed conduit with a rectangular cross section, where you have the lower plate, you have a porous surface, namely a membrane, and you are filtering a solution which will be having molecular weight or molecular size higher, larger than the pore size of the membrane. So, the solutes will be deposited over the membrane surface and forming a concentration boundary layer sort of thing. And we used similarity solution to obtain the concentration profile within the concentration boundary layer, and our objective was stated as that to utilize that concentration profile, how to estimate the mass transfer coefficient. Okay. So, in the last class what we did, we obtained the using similarity solution, we have obtained the concentration profile within the concentration boundary layer. So, in this class we will just wind up that problem, how to apply, how to calculate the mass transfer coefficient using that concentration profile. Okay. So, you write down the definition of mass transfer coefficient. The definition of mass transfer coefficient is simply K Cm minus C naught is equal to minus D del C del y evaluated at y equal to 0. Cm is nothing but the concentration at y equal to 0, that means at the membrane surface, y equal to 0. So, this is basically concentration of solute at membrane surface. So, you know the concentration profile C as a function of eta, where eta is y divided by x to the power 1 upon 3.